Good morning, everybody who are in the lecture hall. We also have people joining us on Zoom, and also people watching us from the future, maybe binge watching for the exam. So in this lecture, we are going to study relational database management systems, so basically how to store data in the classical sense, so the historical way of storing data. Is going to be very useful for many of your research projects that you might do in the future when you need to store and query data. In fact, this kind of data structures, so the relational tables, actually covers maybe 80% of the use cases. So you will see that it's extremely powerful and the good old systems work quite well. Now, today is going to be a bit special because on the first day, I always do some kind of introduction, very high level, giving you a historical perspective. And we are going next week, maybe today if time permits, but otherwise next week, we are going to dive into the material and start looking at the math of relational models. So this is Xiaocheng. He's with me. He's the moderator. He's making sure that if I don't see somebody raising a hand, then you see it and you interrupt me. The same thing on Zoom. If you're watching us on Zoom, you can ask questions by just writing in the chat. And Xiaocheng will also interrupt me so that I answer the question. We really try to make sure that everybody can participate. The lecture is recorded. It's going to be put on YouTube, and then you can watch it later, or even if you cannot attend the class, you can just watch it later. So when I teach database systems, I like to compare it with physics or with chemistry, because in fact, when you manipulate data, it feels very much like you're actually doing some chemistry with the data. And this is one of the intuitions that I would like to give to you. And when I compare them, I like to say that data science is a little bit like physics, right? So when you look at the historical perspective, back then we didn't have any computers. There were a lot of philosophers. And then out of philosophy, you started having two subject matters that started emerging from this. And that would be mathematics and physics, right? And so if you want to very coarsely define the difference between the two, people might disagree with me. Of course, you can talk for hours about this, but mathematics is pretty much what you can just deduce with your brain. The laws of logic, the math, and so on. You can basically do it on a blackboard and from an armchair. But for physics, you have to go out there and experiment. And the difference is that physics is about studying the world as it is and figuring it out, but the world could have been otherwise. The speed of light could have been different. The mass of the electron could have been different. So the only way we can know is to experiment. Now, so this is why I call in model logic that would be necessary and contingent. So necessary means the math has to be the way it is. And contingent means it's neither necessary nor impossible. So it's like it is, and it could have been different. Okay. So now with computers, we kind of were more modern. So now we have silicon and CPUs that can accelerate the whole thing. But contrary to what many people think, in computer science, there's also a lot of theory like on computations, algorithms, complexity, and so on, graphs, and so on and so on. And it's with a machine, but you can still figure it out with a blackboard, right? In fact, there's whole research groups in the computer science department that only use the computers in order to send emails and to write their papers in LaTeX, right? And basically, data science kind of arrived in this last missing piece on the last corner. It's using computers, but it's also about physics, because what we do is we collect data. We just collect data, and then we query it and then figure out something about the world. This is not just an analogy, it's real. For example, at CERN, what they do is there's all the collisions with the LHC. In fact, what is done is they collect data. Petabytes of data get collected. In fact, even more data than that is produced, and they have to throw it away immediately and already filter the data that they need. And then that data is stored somewhere, and the physicists all over the world can access the data and try to find the Higgs boson. But finding the Higgs boson is actually a database problem. You have to analyze the data. So this is why I say that literally data science is a little bit like physics. Something else that I would like to convey in this lecture is that even though when you think of databases, you might think of machines and computers, so it sounds like something that is actually quite recent, but in fact, it's very old, this notion of storing data. And I will even show you how old it is. But for example, Plato already had some wisdom back then that you cannot base yourself just on numbers, but also on knowledge. So it's not enough to just look at the data itself. You need to have models on top of it to extract some information, right? So now I would like to go through a short history of data science or of databases, just to get an impression. Who was in big data for engineers? Some of you. Who was not in big data for engineers? Okay, this is all new to you. Big data for engineers will be in spring again. So if you want to then have the sequel of that lecture, you can later. So this will basically be for most of you new to you. So in fact, databases are very, very old. If I go even older than humans, I would think of the DNA. The DNA in all living beings is basically already some sort of data, right? These four bases like G, C, A, T, that's also a kind of database of our genes. But now if we start with the first humans, so back then the data was just in our brain. What do I mean with data? I basically mean the stories, what's going on with all the people, the kings and the battles and so on. That was just remembered in people's brains, and they would tell it to their children, who would tell it to their children, and so on. So this was all done by speaking. Some of it was also done by singing. In fact, the singing was just in order to help the retention in memory. If you sing, it helps a little bit. But there was a problem with that. And one of the problems is that you can forget things. From generation to generation, a lot of knowledge actually gets lost because it's not going to be repeated sometimes at all. Another problem is that you can start making errors. You can start distorting the reality, and then after every generation, the information is going to be slightly changed. These are the sort of games we play as kids, right, at school, that you repeat something from ear to ear and then see what it became at the end, right? That's a popular game. That was actually solved at some point with a major invention, which was the invention of writing. With writing, people realized that if you would find a way to encode the data somewhere, you can actually keep it over thousands of years. And in fact, this is exactly why, from the moment of writing, this is when we have access to history and we have reliable information on the history. But that only started with the writing because it was preserved as is. Some of it, of course, was destroyed, but everything we found was preserved as is, right? So this was the invention of writing. By the way, the people, even millions of years ago, they were just as intelligent as us, right? So this was, they figured all of these things very early. Of course, they didn't have the same knowledge database than we do when we go to school and then learn everything that people already know. But this was a revolutionary moment when that happens. But there is something even better than that, because this is just text. It's the story of something. But in fact, some of the clay tablets were looking like this. That's not text. That is, in fact, a relational database. It's the oldest relational database that I'm aware of, that we are aware of, right? So how can you see it? It's basically a table. You see rows, you see columns. It almost feels like some spreadsheet software running on an iPad, right? So this gives me the goosebumps when I see this, like seeing this is 4,000 years old, and that is actually already a relational database management system, right? By means of a clay tablet. Does anybody know what there is in there? What that data is? It's actually, you know, when you have a right triangle, the square of one side is equal to the sum of the squares of the other side, right? And you can have that with integers like 3, 4, 5, right? 5 squared is the same as 3 squared plus 4 squared. This is in fact a list of such integer triplets that can be the integer sides of rectangular triangles. That was especially useful, for example, when there was floods in ancient Egypt. Then you need to keep track of who owns what land, and that was done with triangulation, for example, and this is how geometry was actually invented. So you see, this was actual data. This is actually a relational database management system with the domains that are integers, right? If I interpret it in our modern fashion. But there was still a problem with that, is that you cannot make copies so easily. The only way to make a copy is to have somebody just create another one and copy it over. And in fact, for centuries, this is how it was done. Right? Typically in Europe, it was the monks who were basically doing this, making copies and copies and copies. And that was solved also several centuries later with yet another invention, and that is the invention of the printing press, right? And with the printing press, you can just put some small rectangles that have the letters on some machine, and then immediately have it with ink go on paper, right? In fact, I don't know if you were aware of this, but the word in German for letter is Buchstaben, and Buchstaben designates exactly this idea of the rectangle that you put in there. This is what you have here. Another anecdote with this is the reason why we say uppercase, lowercase for the letters is that it was basically all put in boxes like this, and the uppercase letter were in the upper part of the case and the lowercase letter in the lower part of the case. So this is why we say uppercase, lowercase. So that solved the problem of copying the data, because now we are able to print books and newspapers in thousands or millions of copies and very easily spread it into the population. And this is what culminated in the 19th century with the golden age of the press, right? With all the daily newspapers that were very easily and quickly propagated, right? So this is the printing press. And finally, there was more progress made now with computers, but that's actually not so new, but it just accelerates things. Because now with first mechanical parts, and then it was with transistors as it became smaller, we are able to do that much, much faster. But it's really still about storing data and processing data, right? This is still the same idea. So this is a very old computer. It's a few decades old. Not so far away, actually, in the past. But you have to imagine that the power of this thing on the screen is less than the smartphone you have in your pocket. And when you switch it on, the electricity, half of the city is without electricity, right? This is to say the impact that it had on the electricity grids back then in terms of power. So we made a lot of progress. And so that brings us to the 1960s. And in the 1960s, there were the first computers with some storage. And what people did is that they had these directories and files that probably most of you are aware of. But this is how people dealt with data. They would just store them as files on the hard drive and then write computer programs that open these files, read them, and then do whatever they want to do with it. It was very cumbersome to do. So these were the file systems. This is when a revolution happened from the perspective of database systems in 1970. 1970 is the most important year for database people. This is where this person, Edgar Code, had a brilliant idea. And the brilliant idea was that instead of thinking that people should directly read files from disk and write computers program to do that, which not everybody can do, people should be shielded away from that. They shouldn't even have to look at files and to see any programs. Instead, they should only see tables. Why tables? Because they are 4,000 years old. This is something everybody understands. In polls, psychological polls, for example, you ask people, do you understand a pie chart better than a table, a scattered plot better than a table? The one thing people understand best in the world is tables. This is the one universal thing. So the idea is quite natural to say that in a really good database management system, what we should have is people only see tables and manipulate tables, and that's it. All the rest is hidden, right? So this is it. That's the start of the relational era, where this becomes the first-class citizen. It's the same as the clay tablet I showed you earlier, but now it's abstracted in a logical way, right? Then if I continue through history, in the 1980s, that's when you started having languages like C++ or Java that appeared, the object-oriented programming languages. Then people tried to tie them to relational database management systems, which wasn't easy because tables are not the same as objects. But it was a hype back then to do that. Java is more in the 90s, by the way. C++ first, and then Java arrived a bit later. All right, I'm going to stop the history here. It's actually continuing a little bit. I will tell you a bit more, but let's stop in the 80s. That was really for the relational table that I wanted to tell you about. Well, I can still tell you. So this is what appeared later in the 2000s. We had key-value stores, triple stores, column stores, document stores. Now, this might not seem very, I don't know, appealing, but in fact, key-value stores back then were like the blockchain today, right? Or even AI, artificial intelligence, ChatGPT. That's how key-value stores were perceived. Everybody wanted a key-value store. Every company had to have a key-value store, and that was really a big, big hype around this, right? Okay, but this is not part of this lecture. I'm just mentioning that this was done a little bit later. That's actually what we cover in big data for engineers. So a common way to look at data science is to see this pyramid where we have the data, the actual data you have on the clay tablet. Then you have on top of that information, then knowledge and wisdom. So these are all the layers of abstraction. Now, in this lecture, we'll deal with databases, just storing the data and querying the data. On top of that, some other people apply machine learning techniques or artificial intelligence. That's not in the scope of this lecture, but it belongs to the whole ecosystem, right? You can also run machine learning. Actually, knowing relational databases helps you understand machine learning because the notion of a relational table is also in machine learning important when you have the notion of features. Who did machine learning? Some of you, right? So you heard about features, labels, and so on. So you can view that as columns in a relational database. Okay, but in that course, we are going to focus just on that layer, just on storing and querying the data. Now, this is the architecture of the courses that I give. So now this lecture is information systems for engineers, and then big data for engineers in spring. This is like two parts of a movie, right? So you have the good old databases that are still very important today and cover most of the use cases, and then the more recent evolutions covered in big data for engineers. And big data is also now, but this is only for master students in computer science and data science. All right. This is why I would like to test a clicker app with you. So this is something that is developed at ETH. It's a way for me to ask you questions, test your knowledge. You know, I see how you are following. So you have two ways of doing this. You can either go to this address in your browser, or you can go to the App Store or Google Play or whatever App Store you have and look for EduApp 3.something and install it. So either or, right? So I'm going to switch now to the other screen. Right. So just to try to have an overview of your backgrounds. You can participate from the lecture hall. You can also participate from Zoom, right? So this is a good way of having everybody, no matter where you are, you can use this application, right? Okay, so I'm giving you a bit more time for the first time, and then you will know how it works the other time. We have a majority. Wow, mechanical engineering. Who is a mechanical engineer? Studying? Wow, okay. Welcome. We have ETH. Some of you as well. Biology, physics, both theoretical physicists and experimental physicists, mathematicians, maybe CSC is a part of it. Who is a PhD student? Maybe we have some on Zoom. Just so you know, for PhD students, so here it depends on your departments. There are departments who want you to take so you need 12 credit points as a PhD student of lectures, right? Some departments want you to take the exam in exactly the same conditions as everybody else. So then that's you can just attend the lectures, take the exam. Some other departments say that you don't have to take the exam, you just need to have an attendance confirmation, right? It's a testat, what was called a testat back then. If this is your case, you're a PhD student and your department doesn't require the exam, just the attendance confirmation, you need to tell us now or today. So you need to send an email to the TA team and let us know, because we need to check your attendance so that we can issue an attendance certificate at the end, right? This is only about the PhD students. Okay? So I'm going to stop here. Since we are at it, let me also ask you this other question, just to get a feeling. When I say relational databases, SQL, all of that, is it something you've never ever heard of? Or have you heard of it, but don't really know what this is and you want to learn? Have you already programmed in SQL? Maybe some of you have done personal websites, maybe web shops, these sort of things, and then you used a relational database in the background, or maybe some of you did it in Python, using Jupyter notebooks. Do we have people who completely master it, like no secrets for you, 6 normal form, like super experts of SQL? And maybe you want to enhance your some other aspects of databases. Okay, very good. So the majority has heard of it, but that's it. Some people have never heard of it. Well, you are at the right place. You are in the right course, because that's exactly the goal of this course, to make you aware of this, and especially aware of this so that you will have a toolbox for your future research projects at ETH, or even in the future. You will know what kind of system you can use to store your data and query your data, and how to make it fast also, because it's one thing to actually do the queries, it's another one to make them run fast. Okay, very good. And by the way, this is true in every course, right? But classes, especially since you are people from many departments, can be a bit heterogeneous in terms of background and the knowledge you already have. And when there are people who are at the next level, like you, who have more mastery, do not hesitate to help others. There's no better way to learn than to teach, because teaching forces you even more to you see at once what you can still enhance in your knowledge. So don't hesitate to interact with each other and help each other. For that, we have a chat. I will tell you the address. We have the Element chat. We have a forum. So it's a win-win thing. Okay, so let me now switch back to the slides. If I did it correctly, then when I reopen, we should land exactly where we left. Let's see, just has to do its thing. It's loading the slides. And just here, like, yeah, now, okay. Very good. Okay, so this is where we were. Now, I'd like to introduce you to the TA team. Some of the TAs are here. So can you stand up maybe so that we see you? So we have Xiao Cheng here, who is going to moderate the lectures. We have Eugénie here, who is another TA, and we have Andreas also here with it. Are there any other TAs? No? On Zoom? Are there any TAs who joined on Zoom?
Yes, I am here, Martin.
Ah, who is it? Is it Marcin?
Yes.
Ah, hi, Marcin.
Nice to meet you all.
Okay. All right. So why don't we applaud them first to encourage? They will help you throughout the semester. An applause. Yeah. All right. So if you need anything, just write an email. You will have the Moodle forum. You will have the Element chats. and everybody is here to help in the exercise sessions too. So do not hesitate. All right. So what are we going to do in this lecture? So this is the menu. We are going to have a first part where it's the basics. What I will try to do is alternate between theory and practice. So in 1 week, we'll do some math, we'll do some scary theory. Then in a week after that, we'll look at the practice, how to actually use the software and the system to make it work, right? So we'll first start with the relational model, which are the mathematical definitions of a relational table, because it looks simple when you look at a table, but in fact, there is math behind that and theorems. But not too scary, don't worry, we'll work our way through it. Then we'll use SQL to create tables, create schemas, specify the columns, the types, and so on. Then we'll go back to theory, and the theory will be relational algebra. The relational algebra is basically the math of the manipulation of tables. You know that the same thing goes with numbers, right? The model that would be numbers, integers, real numbers, complex numbers, and so on. And then the algebra part of mathematics is about addition, multiplication of numbers, and so on, division. So this is how you manipulate numbers. In fact, we are going to do exactly the same thing with tables. You can define tables, and then I'm not saying you can add table or multiply table, right? It's not going to be addition and multiplication, but you can do things with tables, right? You can define things that you can do. And this is called the relational algebra, so that's the math. And an implementation of that relational algebra is in SQL, which is the language in which you express how you want to transform the tables and query the data. So then we will use SQL, and here you can do it on your laptops, in the Jupyter notebooks, to type your queries. You will see that it's incredibly simple. Just a few lines can be extremely powerful to extract data. Who has ever heard of Pandas or NumPy or all these libraries? Okay. You will see that SQL is even simpler than that, right? Because SQL is a language, Pandas and NumPy, that would be APIs, right? So we'll see a little bit the difference, and then we will make sure that you know how to use SQL to query your data. All right. Then we'll switch to an advanced part. Database design theory is basically how to do things wrong and how to do things right. What are the mistakes you can do when you design your tables? There's a whole theory behind it. We'll cover that theory, and then I'll, of course, give you the intuition and the takeaway messages that we learned from it. Then indices are going to be the study of how to make the database system fast. I can actually give you an intuition of that. You know, at the end of books, when you have, maybe not at the end of a novel, but at the end of a technical book, in the very last pages, you have what's called an index. That index is an alphabetical list of words, and then the pages on which these words appear, right? Who already saw that, right? Most of you. This is an index. What does it give you? It gives you a super fast way of finding where the words are located in the book. If you search for something, you can very quickly find it. Well, indices for databases are exactly the same thing. It's a structure that looks exactly like this inside the system that magically accelerates the query. Without an index, it might take 3 hours, and with an index, 2 seconds, or even a few milliseconds. So it looks like magic, but we'll see that it's actually not just magic. There's ways that you actually make it work. So that's called an index. Then we look at the architecture and storage. So again, it's about seeing that it's not magic, but there's actually a way that the system is actually working. So we will look into this. We will look into the interaction with other languages, because for those of you who have a website with a relational database with SQL, you probably also use another language, like PHP, for example, is a popular choice for websites, Java and others, right? So there's an interaction between SQL and other languages. Then we look at data cubes. Data cubes has a different shape than table. I'll come back to the data shapes. Data cubes were very popular, have been very popular since the 90s. It's about business reports. When in a firm, you need to build the financial reports at the end of every quarter, and then you need to accumulate all your sales data in data cubes and analyze them. So they are really something of their own. So we'll also look at data cube structures, right? And then an outlook towards the next generation of databases with big data. Okay, now what do we have in the course? We have the lecture every Friday from 10 to 12. I really encourage you to attend because that spreads it all over the semester and it's much easier to retain knowledge. Then there is the exercise session. Not this week, today there is nothing, but next Friday will be the first one and the Monday after that will be the next one. So this Friday and the Monday that's coming now, there is absolutely nothing, right? So this is 1 hour, and this is with the TAs. And then at the end, not in, yes, in the winter session, that one I got right, keep confusing them. In the winter session, that means between the 20th of January and the 14th of February, somewhere in this period, we will know probably towards the end of the end of the year, maybe in November, December, we'll get the dates. And then there is 3 hours of exam. Now, don't be scared. 3 hours might sound scary because that's a lot of time. But in fact, the real story is that at ETH, normally, we are not supposed to put you under time pressure for the exam. If we want to assess your knowledge, you should have the time to actually think about the exercises. So what we tried to do, we kept the size of the exam constant. And we extended the time to basically make sure that you have. So many people leave after 2 hours, 2 hours and a half, but that basically gives you time to double check your answers and solve the questions. I will tell you more during the semester about the exam. It's going to be on a computer. It's going to be based on Moodle quizzes. You will have a lot of multiple choice questions, some questions where you need to fill the blanks. You will have some practice questions because on the computer there will be a PostgreSQL installation. That's what we'll learn during the semester, and a Jupyter notebook. And during the exam, you will be asked to solve queries and write the SQL for solving the query. Then you enter the answer in the Moodle, right? So this will explain to you. And what I keep telling the TA team is no more than 60 questions, 60 multiple choice or practical or theoretical questions, right? So this is capped in that way. If you pass the exam, you will get 4 credit points for your transcripts. Okay, but again, the credit points are only half of the reason you're here, right? So many tend to over-focus on the exam. The other half of why you're here is to learn things that will be useful through your entire life, right? So for the project as a student, but also later, this will be very useful having this knowledge even in a company, because every company in the world has a relational database management system. It's very hard not to have one as a company. Okay, either on site or somewhere else. All right, but I'll tell you more about the exam as we go, and you'll see it will be familiar through what we do via the semester. Something else I want to show you is the chat. So I recommend you already go now, if you haven't already, to chat.ethz.ch. Just to log in once. We will invite you to the chat room of the course, and then you can interact here. One of the popular things that people like to do is share memes on the chat. So if you want to do it, and so that you enjoy, the atmosphere of learning databases, and of course you can, then you can ask questions and interact with us, right? If when we invite you, you still don't have access, let us know, we'll look into it, right? So for most students, this is the way you connect. If some people have a different domain, like int, for example, then we might need to invent you through another server, but this is basically it. You need to click on the right of the page, because that page has 2 sides. There's the staff and the students, so you need to go to the students' chats on the right. I know you also have other chats. There's probably a Discord or whatever. We don't have access to it. So if you want to interact with us, you really should use this chat. Okay. Then the material of the course, the slides, everything will be in the Moodle. So this is the address. You can also access it from the catalog. You'll have all the slides of today and every week, the exercises, the Jupyter notebooks, the old exams, and so on. Everything is going to be stored in this Moodle, and you should automatically have access. You just need to make sure you register in My Studies first. All right, so this is the overall. So now let's look a bit more into some very high-level considerations about data. Basically, what I want here is mostly put the right terminology in your minds, right? What is called what, so that you know the levels of abstraction. So basically, what we store in a database is basically information in order to support our decisions, in order to also help our memory, because if we want to retain all of the orders of a company or the inventory of the company, it's hard to have it in our minds. So we want to store that information. Can be language, written or spoken. A recording, for example, can be drawings, diagrams, symbols, models of the world, and so on. Physicists, for example, do that. And that's really something you could consider like some sort of material, like the flower that you see here. And in fact, the difference between information and data is a little bit like the difference between flour and wheat, right? So this is why I put these pictures right here. The data, the raw data, is actually more like wheat, and you know that you make flour out of wheat, right? So this is how it's made. So the raw material is the wheat. So what is the wheat for database systems? Well, we use the wheat in two ways, basically. We store it and we exchange it, right? So we can store the data somewhere. You might have computers in a data center or wherever, and you store the data there. This is one place where you can store that wheat. The other thing that you might do with the wheat, the data wheat, is to exchange data. What do I mean with exchange data? I really mean like something downloading from a website, right? I'm sure you've already been to a website, I don't know, like the Federal Statistics Office, or where there is data, right? Probably during COVID, a lot of people looked at all the data there. Well, very often on these pages, you have links that allow you to download the data. Very often you see CSV, JSON, XML. Who already saw that? You know, CSV, JSON, XML rings a bell, right? This is exchange of data. Instead of storing it, you send it over the internet and then you store it somewhere, right? So these are really the two aspects of how data is handled. You can store it and you can exchange it or download it or upload it over the internet. Okay, and then you can extract wheat from it. We'll see how, and then this actually becomes information. But the data itself is really just bits. It's zeros and ones. It's really what you have in the files that are downloaded or stored on a drive. Okay, and then there's this whole pipeline from the wheat to the flour to the bread, where you turn data into information by adding some meaning, some context. And then when you start applying it to a real application, like a web shop or you know, a Wikipedia or whatever, then you have a meaningful application, and that's where you have the actual usable output, right? Like this loaf of bread that I put in there, right? So this is really this analogy. Now, the name of the course is Information Systems for Engineers, right? I could have called it in many ways. I could have called it SQL for engineers or relational databases for engineers and so on. But information systems is actually more general, because the name information systems really means it's a computer system. It doesn't have actually to be a computer system, any system that helps you manage your information. An example of non-computer system would be the clay tablets, or it would be, you know, the libraries. They have existed for centuries, and the libraries maybe did it on paper before, but they have this inventory of the books they have, right? That is also an information system, right? But the modern information systems are actually computerized. So it's a program or a set of programs that manages information, right? So now we know what data is, what information is, and what an information system is. Now let's look at the notion of data structure. What does it mean to have structured data? Well, on a very high level, I told you that data is a little bit like chemistry. Data has shapes. It's something that many people, even specialists, do not necessarily put on the forefront of databases. But in fact, shapes, understanding shapes is absolutely fundamental. Why? Because this is going to decide how productive you are dealing with your data, but it's also going to decide how fast your query is going to be. Understanding shapes makes the difference between a query taking 2 days to execute or 2 milliseconds to execute. That is why shapes are so important. You put your data in the wrong shapes, that's going to take much longer and you're going to lose time. You pick the right shape, it's going to be much faster. But the good news is that there are not so many shapes. There's tables, there's trees, there's graphs, there's cubes, and there's text. These are the 5 fundamental shapes. We are going to focus obviously on tables, but there's other shapes out there. This one now, this is the hype at the moment. This is basically ChatGPT and LLMs. We have a new kind of database called a vector database that basically stores mathematical vectors. But this is a different lecture. It's taught in information retrieval for computer science students, right? So these are the 5 fundamental shapes: tables, trees, graphs, and cubes. Cubes we'll study too in this lecture, so tables and cubes, okay? You can actually arrange them in some spectrum, all of these, right? From structured to unstructured. The most structured data you can have, that's basically the cubes. This is as structured as it gets. Tables are also considered structures. Trees, this is basically XML and JSON. That's what I mean. This is in between. It's semi-structured. We are not going to look at them in this course. Graphs are a bit less structured. A few years ago, that was also kind of a hype, the graph databases. And text is as unstructured as it gets, even though now we know better how to handle them thanks to vector databases and the progress in LLMs. But this is it, right? So this is the spectrum between unstructured and structured data. What's the intuition behind that? I would say that the more structured the data is, the easier it is to handle it. When data is structured, it's super easy. When data is less structured, then there's more complexity and it's a bit more of a challenge, which is exactly why the text was the last one to actually have made it through the ladders of database systems. Okay, so make sure you remember that, the structuredness. And again, we are going to look in this course at the structured sides of things with tables and cubes. Okay, so unstructured data would basically be text like this, which now we store as vectors, with ChatGPT. But in fact, we can also have images that are just pixels that could also be considered as unstructured data. Here too, very recently, we make progress with generative AI, and now you can just write a prompt and get an image, or you can even have computers tell you what there is on an image. So it's really amazing in just a few years, the progress that we've made with that. Audio, and that's the same with speech recognition. Now you can interact and speak to machines. Videos, which are sequences of bitmaps, it's one of the oldest ones. So basically, unstructured data is very raw. The reason it's very complicated to process unstructured data is that it doesn't have anything explicit. It's just words or pixels. In structured data, you have explicit meta information. For example, in the tables, you have headers on your table. You might have a list of people. You're going to have the first name, the last name, the birth date, and so on. These are explicit features that you have in structured data, but you don't have that in unstructured data. You just have characters and pixels and waves and so on. So this is what makes it complicated. Semi-structured data is a little bit in between. So you see that this is a tree, for example, on the left. XML JSON can be seen like this, or YAML, yet another markup language, YAML. Data frames are a specific form of these trees, but you see it's not quite a table. You see that it's not exactly a table because the lines, the rows and the columns, they don't run the whole way, right? You can see here that there's a line, but here it doesn't go through. It's like merged cells in a spreadsheet. So this is what is called a data frame. If you use pandas, then you might actually know a little bit about these data frames. Well, the tables are even more structured than data frames because in a table, the lines really go through the entire row and through the entire column. Okay. And finally, structured data. So structured data is very commonly people think of tabular data, so tables. This is an example taken from finance, from the stock market, where you have columns like the company name and so on, right? It's nicely organized in columns. It's even beautiful to the eye, right? When you see structure like this. All right, so this is what we're going to study. It has a fixed structure. The structure is defined in advance. Even if this has a life and new companies are added and the prices change, you still have this structure, the company, the change last, and so on. It's defined in advance. That's called a schema. I'll come back to this. All right, and in fact, this is what will bring us to relational databases or spreadsheets, right? I will often use the comparison with spreadsheets because I assume who use the spreadsheet software already? Excel, LibreOffice, or whatever, right? Many of you. So I will try to use analogies as well. I think we should have a break. Today is not very complicated, right? It's just high level. It's just the appetizer. But still, let's take a break. 15 minutes. We'll continue at 15 past 11, quarter past 11, and I'll continue to drive you through this high level. Thank you.